In this video we are going to introduce the topic of surface area and volume of three-dimensional objects, with the particular focus on surface area in this video. So firstly, a few definitions and a bit of theory. We need to know that a solid is simply a synonym for any three-dimensional object. In the previous chapter, or the previous topic, we focus on two-dimensional shapes that we also refer to as plane shapes, where there was no thickness. Example would be the page in your book. There's a length and a width, but not really a thickness or a height. So for three-dimensional objects, we just have the added dimension of height. So this is a solid as it has a width, a length, and a height. Next, we need to know what a polyhedron means. It is a solid in which all the surfaces are flat. Poly we know means many. So it is basically many flat surfaces if you translate this directly, the polyhedron from Greek. So a solid in which all the surfaces are flat. So we call these various surfaces the face of the solid. So we refer to the face. So here's a face, on the side is another face, here's another face, at the bottom is a face. So if we think, for example, of the classroom we are in, let's just think, how many faces will there be? Well, there's the roof at the top, that's one face, or let's call it the ceiling rather at the top, that's one face. The floor at the bottom is a second face. Then the wall in the front is a third face, the wall at the back is a fourth face, the wall to the left is a fifth face, and the wall to the right is a sixth face. So there are 6 faces in our classroom. Next concept is that of an edge. That's basically where 2 faces meet together. So for example, this line here will be an edge because we have faces meeting. We have 2 faces meeting at this line. So another example of an edge will be here. This is maybe a better illustration because we have this face meeting this face at that edge. And then, other than edge, the third aspect that we need to know is a vertex. So vertex is in fact where 3 or more edges meet. So for example, here we have a vertex. So we have 1, 2, 3 faces meeting. So basically, if you think of our classroom, the corner at the top of the ceiling or the corner at the bottom at the floor, where we have, so if we take the one at the bottom of the floor, we have the floor meeting 2 of the side walls. That would be a corner. Next, we need to know what a prism is. It's also a solid, in other words, a three-dimensional shape that has at least one pair of congruent parallel flat faces. Now, congruent we know means exactly the same. If you have 2 congruent shapes, you can put them on each other. They will be an exact match. Okay, so that's congruent. Parallel means they are the same distance from each other at 90-degree angles. So we also need to to distinguish between a regular prism and an irregular prism. So a regular prism is a prism that has a regular polygon as its base. So let's first explain what regular means. Polygon, we know it means many angles. Poly means many. So polygon has many angles or many sides. So regular polygon as its base. So now we first need to know what a base is. The base of a three-dimensional shape is basically the top and the bottom face. So in this case we have a triangle at the top and a triangle at the bottom. So in this example, we have a rectangle at the top and a rectangle at the bottom, so it has rectangular bases. This one has triangular bases. So we now know what a base is. So let's look again at the definition of a regular prism. A prism, okay, so first let's think of what a prism is. A prism is a solid that has at least one pair of congruents. So congruent, if you take this triangular prism, it means the top triangle and the bottom triangle will fit exactly on each other, okay, which we can see this is the case. So it's a prism in that sense. And parallel, okay, so these two triangles are parallel because they are the same distance from each other when we have 90-degree angles from the bottom one to the top one. So at any given point, if we take a 90-degree from the top to the bottom, and we take any other point like a 90-degree from the top to the bottom, then these two lengths should be the same. So it's not tilted or anything like that. So we can see this is therefore a prism. But now a regular prism is a prism that has a regular polygon as its base. So the base is the top and the bottom. So we look at the triangles. Regular means in fact all three, the sides are the same length. So here also regular means all these sides have the same length. Regular means this should be a square as all four sides have the same length. So now an irregular prism is a prism that doesn't have regular polygons as its base. So now you have different lengths for the sides. Well, these two might even be the same, and these might be the same, but this length and this length isn't necessarily the same, and this is also a different length than those. The fact of the matter is all the sides don't have the same length, then it is an irregular prism. Next, we need to know what a right prism is. So it's a prism that has two bases directly above one another and whose other faces are rectangulars. So two bases directly above one another and whose other faces are rectangles. Now prism is named after its base. In the previous slide we saw we had triangular prism and then we had a prism with right angles as bases. So now a cuboid is a rectangular solid with 6 rectangular flat faces. So the base we know is the top and the bottom. So we can see the base are rectangulars. Okay, we can also see it's a right prism in the sense that the other faces that connect these two base rectangulars are also rectangles. So this is what we refer to a cuboid, since we have rectangular bases. A cube is a rectangular solid with 6 square flat faces. So Now all of the faces are squares, so you can see all the sides have the same length. So if all the faces are squares, we refer to it as a cube. And then a triangular prism is a prism in which the two parallel bases are triangles. So we can see the base on the top and at the bottom are triangles, and it is a right prism as rectangles connect these bases. Even for the cube, remember a square is a form of a rectangle. So even here you could say the other faces that connect the top and the bottom bases are rectangulars. A very specific rectangle in this case, namely a square. So next we need to know that what a net is. It's a two-dimensional shape that can be folded to form a three-dimensional object. So here's an example of a net. We can fold it so that it becomes a three-dimensional shape. So now we get to what's really our focus, and that's the surface area. It's the total area of all the surfaces of a solid. So here we have a solid. We have rectangular faces which connect two triangles. So very important here, our bases are rectangles. So we could flip this around so that at the bottom we have a rectangle and at the top a rectangle, because remember, part of the definition of a prism is that we need congruent bases. So the two triangles can fit on each other, so they are the congruent bases. And then what connect them are rectangles. So we also know this is a right prism per definition, as rectangles are connecting them. So now we can see the relationship, in fact, between nets and solids. The reason why we would want a net is it makes it easier to determine the surface area of the solid, because now we can see all the faces and we can insert all the dimensions. So we have 1, 2, 3, 4, 5 faces, of which we need to calculate the area of each one of them and then add them up to get the surface area of the three-dimensional shape, which in this case is a triangular prism. So now, with all the theory behind the back, let's have a look at exercise 17.1 to illustrate some of these concepts. So given this is a triangular prism, we can see it is because we have two congruent triangular bases. So in other words, we could tilt this so that the triangle is at the bottom and the triangle is at the top, connected by rectangular faces. So is it a regular prism? Explain why or why not. Yes, it is a regular, because remember, what's the definition of a regular? It means that the sides of the bases are all of same length. And here we can see we have our symbol that shows that these three sides are the same length. So all the sides of the base of the bases are equal in length. So in other words, we actually have an equilateral triangle as the base. So number B, we need to name the end faces or bases of this prism. We actually just answered that when we indicated that it is triangular. So it's equilateral triangles. So it's triangles as bases. Next, we need to know how many lateral faces does it have. Now, lateral, that refers to the rectangular faces. The lateral faces are the faces that connect the bases. So it doesn't include the bases. So it's not the two triangles, it's the remaining faces. And now since a triangle has three sides, we will have to connect the one triangle's three sides with the other triangle's three sides by a rectangle. So we are going to need three rectangles. So there are three lateral faces. Finally, is it a right triangular prism? Well, per definition, a right triangular prism has lateral faces that combine it. And it is parallel. So yes, it's basically parallel. So we have parallel. I think somewhere I have L too many. I have an idea it's this last one. So it's parallel. So we have parallel, congruent bases connected by lateral, by rectangular, or by rectangle lateral faces. So yeah, the answer is yes. We have parallel congruent bases connected by rectangle or rectangular. I think rectangular is the proper English. Lateral faces. So now let's do some calculations. We need to calculate the surface areas of these solids. Okay, so first of all, what solid do we have here? Well, we need to look at the bases at the top and the bottom. So it's rectangles. So this is a rectangular prism. So now let's see. We have, so the top and the bottom face, namely the bases, will be the same. They are both rectangles. So our surface area, SA for surface area, will be the area of this top face multiplied by 2, as the bottom face looks exactly the same. So we can say to get the area, it's length times breadth, but in this case we have two lengths, 2 times the length times breadth, as the top and the bottom one is the same. And then we can look at the two sides on the right and on the left. They are the same, so it will be the same concept there. And then this one and the other one on the other side, they are the same. So we are going to have to do 3 calculations and each time multiply by 2. So we can in fact say the surface area is equal to 2 times 315 millimeter times 98 millimeter plus, if we look at these ones, it's 2 because it's 1 on both sides, so it's 2 and the dimensions there is 126 millimeter times 98 millimeter. And then finally we have these ones here and on the other side, which is the 315 by the 126. So it's 2 of them, it's 315 millimeter by the 126 millimeter. So the pattern that you can see is we actually just have various combinations of the sides. We have a 315 times a 98. We also have a 315 times the 126. We have a 126 times the 98. We also have a 126 times the 315. We have a 98 times the 35. We also have a 98 times the 126. So it's just all the different combinations in fact. So let's just get our calculator to do some of the calculations. So we have therefore 2 times 315 times 98, which will give us 61,740, and our millimeter times millimeter is millimeter squared, plus we have 2 times 126 times 98, which is 24,696 square millimeter, plus we have 2 times 315 times 126, which is 79,380. Millimeter times millimeter is square millimeter. So all our square millimeters, we can therefore add up the 3. So we have the 79,380 plus the 24,696 plus 61,740, which will result in 165,816 square millimeter. So let's look at number 2a now. In this case, we have 2 congruent bases connected by rectangular lateral faces. So this must be a triangular prism. So the top and the bottom will be the same. So we can calculate the area of the triangle and multiply by 2. And then we will have the rectangles areas that we also have to calculate. There are 1, 2, 3 rectangles. So but it seems like, so in this case it's a regular prism, as all these sides are the same length, 560 millimeter. So therefore, the rectangles that connect the sides of the triangles will all be the same, have the same area. So we will have to calculate the area of the triangle, multiply by 2, calculate the area of one lateral face and multiply by 3, as there are 3 of them. As a triangle has 3 faces, therefore the 2 triangles need to be connected by 3 rectangular faces. Add up, and then we will have the surface area. So the surface area is in fact 2 times, let's first get the triangle, there are 2 of them, and we know the area of a triangle is half base times height, so we can say we have 2 half bases times heights, plus we have 3 rectangles, and the rectangles area is length times breadth. So we have in fact now 2 times a half, the 2 just cancel out, so that's 1. So we actually just have the breadth times, or the base times the height. So our base is 560 millimeter, so we can replace our base by 560 millimeter. The height is indicated as 485 millimeter. And now we can look at our rectangle. There are 3 of them. We have a length of 980, so it's that distance, and then we have the 485 for the breadth, for the width. So it's 3 times the 980 millimeter times the 560 millimeter. And now it's a matter of doing the calculations. So we have 560 multiplied by 485, which is 271,600. Millimeter times millimeter is millimeter squared, plus 3 times 980 times 560, which gives us 1,646,400 square millimeter. Now we can simply add up. So we have 1,646,400 plus 271,600. 271,600 equals 1,918,000 square millimeters. So the important thing that we see is surface area, just as area is measured in square units. Another way to actually think about the surface area is to think of this as something that needs to be gift wrapped. And the question is basically, how much paper are you going to need to gift wrap this object? You'll see that is important to distinguish surface area from volume, which we will soon cover. Because volume is not about the outside and wrapping, that is about what can we fit inside. That is when we refer to volume. So your task is to do number 3 of exercise 17.1. I'm sure you won't battle with that. Let's have a look how you are doing. It's basically fitting nets or matching nets to solids or three-dimensional objects.